Hey everyone, you know that stunning iridescent finish on your favorite sunglasses or the super tough, scratch-proof screen on your phone? Well, that's not just some fancy paint job. It's an amazing technology called sputtering, and it's where art and science literally collide on an atomic scale. So let's dive in.
The answer is just fascinating. I mean, that deep metallic sheen on your laptop or the vibrant anti-reflective coating on your glasses, it isn't paint at all. It's a masterpiece of physics, engineered one single atom at a time, using a process called sputtering.
And honestly, that atomic spray painting analogy is the perfect way to picture it. You've got this vacuum chamber where ions bombard a source material, knocking atoms loose. These atoms then just fly across and land on a surface as this perfectly uniform, ultra-thin layer. We're talking about precision at a scale that's almost impossible to wrap your head around.
All right, so sputtering isn't some one-size-fits-all process. The two main workhorses of the industry are DC and RF magnetron sputtering. These are the foundational techniques, and which one you use really depends on what kind of material you're trying to coat.
So here's the key difference. DC, which stands for direct current sputtering, works great for things that conduct electricity. Think of it as this steady, constant stream for metals like copper or titanium. But what about insulators, right? Stuff like glass or ceramics? For those, you need RF, or radio frequency sputtering. Its alternating field can handle materials that don't conduct electricity, like your metal oxides and nitrides.
And the performance you can get is just incredible. With RF sputtering, you can create coatings that achieve over 90% light transmittance. What that means is you get this invisibly tough protective layer on your phone or computer screen that's both durable and perfectly clear, so it doesn't distort the image one bit.
Now, putting down a single layer is powerful, for sure, but the real magic, that begins when you start stacking them. This is where scientists really become like atomic architects, building custom materials and adding all sorts of new functions just by layering different elements. And this brings us to something called multi-target sputtering. It's pretty much exactly what it sounds like. By switching between different source materials inside the chamber, you can build up a film layer by layer, almost like you're making an atomic scale sandwich. You know, a layer of titanium, then a layer of nitrogen, and on and on.
This layering technique is just incredibly powerful. These stacks of ultra-thin films can actually manipulate light, creating those stunning interference colors that seem to shift as you look at them from different angles. And at the same time, they can be engineered for toughness. For instance, alternating layers of chromium and chromium nitride creates a surface that's exceptionally resistant to wear and oxidation.
Okay, now let's kick this up a notch with reactive sputtering. In this case, instead of just depositing a material, you introduce a gas, like oxygen or nitrogen, into the chamber. The sputtered metal atoms actually react with this gas on their way to the surface, forming a completely new compound. You're not just moving atoms anymore, you're basically doing chemistry in midair.
And the results are just stunning. By creating very specific titanium nitrides or oxides, you can precisely tune a surface's color. But you can also build in new functions, like creating super hydrophobic, water-repellent coatings. This process lets engineers dramatically increase a surface's hardness and its reflectivity, a total game changer for industries like automotive and architectural design.
So with all these different techniques, engineers essentially have this ultimate control panel. They can really act like atomic-level artists, fine-tuning dozens of variables to get the exact aesthetic and functional properties they're looking for.
So how is this level of atomic control even possible? Well, it all comes down to meticulously managing the process parameters. You can think of the vacuum chamber like a high-tech kitchen, where every single variable, from the temperature to the gas mix, is a dial that can be turned to perfect the final recipe. For example, if you increase the sputtering power, you can make a copper film more lustrous just by creating smoother grains. Adjusting the gas composition, say the amount of oxygen, that directly controls a film's color and its transparency. Even the temperature of the thing you're coating can enhance the gloss, while something called a bias voltage can refine the film's structure, making it harder and shinier. It's a really delicate dance of physics to get that perfect finish.
So when it's all said and done, it's pretty clear that sputtering is about so much more than just a pretty surface. It really is the ultimate merger of aesthetics and function, where beauty and high performance are engineered together, right from the atomic level up.
So, what this all means is that sputtering delivers the complete package. It creates surfaces that are not only beautiful, with colors engineered to perfection, but are also crystal clear for our displays, incredibly durable, and highly functional with properties like anti-reflection or water repellency built right in from the start.
And all this just leaves us with a fascinating question for the future. We are literally learning to paint with atoms, to build surfaces that are smarter, stronger, and more beautiful than anything we've had before. As this technology evolves, what new functions will we demand? What new aesthetics will we discover? The possibilities? Well, they're only just beginning to unfold.